Okay, here we go. These, like I said last time, the subject exam is basic knowledge of every possible concept, which means that anybody who is prepared for it, first year chemistry class, didn't learn anything. Okay, because they spent like 1 or 2 days on stoichiometry. So you guys are better off on that from that end. The next 2 or 3 weeks, we are doing bonding. So I'm not going to cover anything related to orbitals or Lewis structures or anything because you're going to get that from me in class. Okay, I'm not going to cover molarity, I'm not going to do stoichiometry, I'm not going to do gases because you got that last year. Anything you've gotten before, I'm going to let sit just for time frame. So you guys can go and review those things on your own. When I say gases, I mean P equals nRT and boils and all that kind of stuff. Alright, so last time we talked about nuclear chemistry and we talked about how in chemistry nuclei can break apart and can release particles. What were some of those particles that they could throw out? Alpha and beta and all that kind of stuff. And we drew the isotope formula and we said that we just need to make the numbers the same. And whatever's left over is stable. Okay? After that, we looked at periodicity, like what makes an atom big, what makes an atom small. What about when we had an ion? Say you had a positively charged ion. Is that bigger or smaller than its neutral counterpart? Smaller, because it's got less electrons for the nucleus to wrangle in. Okay? Vice versa, if it's negative, it's going to be larger because there's more electrons to wrangle in. We then went and looked at kinetics and speeds of reactions. So let's go back and let's look at that a little bit. Let's revisit that. Remember when we had this chart, we put energy here, and we had like a reaction. Let's say this reaction was A goes to B. What did I say this was called? That's called the activation energy. Okay, it's the energy it needs to go over the hill before it can activate or go over to products. And what does the catalyst do to this? And how does it speed it up? Does it push it over the hill faster? It makes the hill smaller. Metaphorically, what it's doing is it's taking it on a new path that requires less energy. Now this distance here, this was called delta what from last time? H. And delta H in this case is less than 0.
So Mr. Krieger, please call extension 791. Thank you.
And if we ended up higher, delta H is greater than 0. And that's what a catalyst would do. So this would be a reaction that's exothermic, and this would be a reaction that's endothermic. Is that okay? Okay, so we're going to launch into right now a topic in chemistry that plays around with delta H, but not just delta H, a couple other really, really important variables. And I'll tell you what that topic is called. It's called thermodynamics. Okay, thermodynamics does not deal with how fast a reaction happens. It does not deal, and remember this is recording my voice right now, does not deal with how fast it happens. It deals with if it happens spontaneously. Okay? So it answers the question, does a reaction happen spontaneously? When I write that word out, what does that mean to you? You know that word spontaneous? On its own. Perfect. On its own. Just have it on its own at whatever temperature and pressure the environment is at. So, an example of a spontaneous reaction. I'm walking right here, and suddenly a bunch of methane comes out of my butt, right at far. That just happened spontaneously. I didn't have to do anything, it just happened. We all have dads that are nasty, right? And sometimes they'll just like, bust the ass and just like, alright? That's spontaneous. That's actually good. What's a reaction that's not spontaneous? Oh, baking like a cake, right? It's not just gonna bake on its own. You gotta put it in the oven and you have to bake it. Or a great example is this right here. Right? So I got all my methane bubbles wait a sec, that's methane and that's oxygen. Is this reaction happening? No, it's not happening. That reaction is non-spontaneous. Okay? In order to make it happen, what do I have to do? Right? I have to light the bubbles. Right? I have to make it happen. And God made that reaction, Catholic school, right? God made that reaction non-spontaneous because that would suck if every time something that was flammable touched oxygen, it blew up. I mean, holy crap, can you believe that I am walking through stuff that burns me? We are walking through air. Oxygen burns us, but we're not getting burnt because that's non-spontaneous. Okay? So, there is a symbol that tells us if a reaction is spontaneous or not. Okay? And that symbol is delta G. Okay? And delta G is called Gibbs free energy. Okay? You're going to be inundated with delta G before Christmas break. Thermo is the unit we're doing in December. Okay? We're going to start with it. Thermo is cut and dry. It's not a big deal, but there's a lot of triangles flying around there. A lot of deltas. Gibbs free energy is delta G. Focus on this word free. How do you think this word free relates to that word spontaneous? If something is spontaneous, it's free. It just happens. Right? Water falling down a dam. Free. It's just doing that spontaneously. So then we use that to do things that are non-spontaneous. Think about PG&E. PG&E takes water flowing down a dam, and it uses that free energy to stick a bunch of electrons in a box. Why do electrons not want to be next to each other in a box? They're the same charge. They're all negative. They want to get away from each other. So all the water flows down the dam, it turns this engine. The engine takes all the electrons and sticks them in a box. And then they sell those boxes to you. You buy the box, and then every time you stick something in the wall, the electrons go away from each other. And that's what paying your electricity bill is. It's letting PG&E re-stuff up that box with electrons. And they're doing it from some dam. That's how it all translates. But it starts with the free energy. But that's where it comes from. Why do you think you get electricity when you put something in a wall socket? It's because the electrons, like Calvin said, don't want to be near each other. You give them a path to move away from each other, they're going to do it. Okay? So, Gibbs free energy is delta G. And delta G has two signs. Delta G can be greater than 0, and delta G can be less than 0. If delta G is greater than 0, a reaction is non-spontaneous. The burning of your skin by oxygen in the air is non-spontaneous. Now you might have all heard of the term spontaneous human combustion. You could call that delta G negative human combustion if you wanted to, which is ridiculous. It's not going to happen. Okay, don't worry, you're fine. Don't be afraid to walk around. Don't be afraid to live in the world. Oxygen is good. Okay. Okay. And this is spontaneous. Okay, so this is one of the factors. This is pretty darn important. So if I were to say to you the reaction has a delta G of negative 340 kilojoules per mole, is that reaction spontaneous or not spontaneous? What if I were to say is that reaction fast or slow? You don't know. You don't know. This thing is going to fall spontaneously fast on Earth, and it's going to fall spontaneously faster on Jupiter, and it's going to fall spontaneously slower on the Moon, because all those things have different accelerations due to gravity, right? But it's still spontaneous. It's still a spontaneous reaction. Okay, don't worry about speed. Now there's another factor that we're going to be thinking about, and I introduced it to you strategically a second ago, and that is delta H. Just going to box everything here because they're going to become important later. And delta H stands for this thing, enthalpy. This is the one factor that you guys learned about last year. And we know these are pretty simple. Delta H is less than 0. What's that called? Exothermic. That means heat exits the room, or heat is released. And delta H greater than 0 is called endothermic. That means heat enters the room. Now here's the thing that's hard for people to understand with this whole thing. This feels hot. But this feels cold, which is hard for people to reconcile when the definition of it is absorbing heat. Why would something that's absorbing heat feel cold? So it has to do with what you as a human being are allowed to touch. So I'm going to draw a little picture here that I think represents it really well. Okay? Okay. This is the reaction. This is the surroundings. This is your finger. Okay? So what are you guys allowed to touch? The surroundings. You're not allowed, you don't get to touch the system. So, if the reaction releases heat, what do you feel? You feel your finger getting what? Hotter. So that reaction is what? Exothermic. Great. Now, the opposite is true. If this reaction absorbs heat, what's your finger going to feel? Cold, because it's taking heat from the finger touching. That's why, so that this situation here, this is delta H greater than 0, and this situation here, this is delta H less than 0. Okay, guys? Okay? So that's why. You might get a question where they'll give you some information, and one of them will be like, a student touches a cold pack. Right? You know, you click it and it gets cold. That's because when you click it, a reaction's happening that's taking heat from the surroundings of the cold pack, and you feel cold. Okay? What that cold pack is it's ammonium nitrate mixed with water. That's it. That's an endothermic reaction. And the hot pack is calcium oxide and water, which is also basic, right? And you guys remember the temperature rose in that circumstance. All right, there's one more factor now to thermodynamics that goes beyond G and H. Remember I said there's a lot of triangles floating around. There's this factor called delta S. And delta S is called entropy. And what entropy does is it's a measure of disorder. So in the world, this is kind of good, right? Like, let's look at how they connect together. Okay? When I farted, did that make the world around me more ordered or more disordered? Disordered. But did that happen spontaneously? Yes. Does your room get spontaneously more disordered or spontaneously more ordered? Disordered. So it turns out the things that make disorder, although making things ugly, actually are spontaneous. So we can use that disorder to fuel order. I mean, follow me, like water falling down a dam. That's getting more disordered. It's all going from here, splashing on the ground. But that's happening for free. So we can use that energy to do things that need energy. Think about Monsters, Inc., right? The monster walks into the room and startles the kid. What does the kid do? Screams. Disorder or order? Disorder, spontaneous too. They took that scream and put it in a bottle. And now they have energy. So we can take things that happen spontaneously and we can stuff them into boxes, and that's how we get energy. A windmill. The wind is blowing it spontaneously. The wind is disordered. Okay? Blowing it spontaneously, we're grabbing that order. Okay? So when we think about delta S. These are all metaphors I'm throwing out right now, okay? So don't get too dogmatic about them. So if delta S is greater than 0, that means that entropy is positive. So that means the reaction produces disorder. And here's the way that you can also think about it. Is the reaction gets messy. That's one way of thinking about it. Now, if delta S is less than 0, the reaction produces order, and instead of saying gets messy, what can I say here? It gets clean. A reaction that gets clean is one like this. So now let me just show you what I mean. What the hell do I mean by that? So solid, liquid, we can put aqueous here, going to a gas. Which side do you think is the messiest side? The solid side or the gas side? Gas. Gases fly all over the place. They're messy. Think about my fart. Okay? So if I fart, that's going to be the messier side. Doesn't make much sense, but if I take a big crap on the ground, that's cleaner in terms of thermodynamics. Because the molecules in that big crap are ordered into crystals. Gross, right? Now there's subliming. Sublimation is happening and it's producing a gas, which again is now messy methane. That's happening naturally. But this side is clean. So here is one way that people go about doing problems about this. Here's a standard example. Okay, so let's talk about what we have just been doing in class. I'm going to take the decomposition of a chlorate and I'm going to make this. Now, what is going to happen, the reason I did Fourier response 4 at the beginning, we're actually going to backtrack all the way back down to bonding next unit. But the reason I did Fourier response 4 at the beginning and molarity is because now, on every single test, I'm going to give you Fourier response 4 questions. So now you'll never forget it. You're always going to be inundated by it. Reactions are going to be part of your life now. So we're going to be doing Lewis structures and polarity next, but you're going to answer Fourier response 4 questions. But the question that I asked you is going to be different now. It's going to be related to the current unit we're on. Okay, so I'll ask you questions like draw the Lewis structure of carbon dioxide now for the question instead. But when I get to thermodynamics, I'll ask you questions like this. So I'll literally say to you, the decomposition of sodium chlorate. If you don't know it now, you know it then. You know, if you didn't get it right out of the test, you'll definitely get it right at the end of the year. But I'll ask you a question like this. What is the sign of delta S for this reaction? That's what I'll ask you. Okay, so when we look at this, there's a solid here, and here we have a solid and a gas. So does this reaction get messy or clean? It gets messier. I got a solid here and I have a solid plus a gas. So that gas right there is telling me that the delta S of this reaction is positive. It's got a positive delta S. So the chances are that this reaction is probably a reaction that has the potential of being spontaneous. Doesn't mean it is, but it's got the potential of being spontaneous. Okay, let's look at a reaction that's non-spontaneous, and then I'm going to tell you a little story which is going to lead into the major equation. Okay, we can take a reaction like this, and thank God this is non-spontaneous. Hydrogen gas plus oxygen gas produces H2O. Well, give me two names for this reaction. Redox? Synthesis. All right. So I have two gases here and I have one liquid. So the reaction started off messier, but it got a little cleaner. So what is the sign on delta S for this reaction? What's that? Less than 0. Delta S is less than 0. So when I think about that, this reaction maybe is getting cleaner, so it's probably a reaction that's not going to end up being spontaneous. And that makes sense because we don't want hydrogen to just blow up every time we're around it. We don't want that just to happen. You guys with me on that? All right. So let me show you a reaction right now. We're going to derive an equation right now that I love. Okay. So I don't know what to title this with. I'll just write the reaction. So if we have the decomposition of sodium carbonate, what two things do we get? Sodium with sodium oxide, or what else? Okay. So, what do you think the sign of delta S of this reaction is? Why is it positive? Forms a gas. There's more gases on the product side. Okay, more gases on the product side here. So this reaction gets messy. So for all intents and purposes, this stuff here is called baking soda. Now baking soda is actually this. Okay, but it makes this demonstration a little bit easier. If this breaks up, you actually get water also. So don't worry about it. Okay? It's the same exact concept. So give me on this. Here's the fascinating thing about this. When I look at this reaction, my prediction is it's spontaneous because it gets messier. Meaning it just happens on its own. But it turns out we know it's not. Because when we go and buy baking soda, is the box bulging and ready to blow up because it's full of CO2? No. Hell no. So this reaction is spontaneous. Baking soda is created to be spontaneous at about 300 degrees Fahrenheit, and to be non-spontaneous at temperatures below 300 degrees Fahrenheit. So what does that temperature remind you of? What is 300 degrees Fahrenheit about? 350 degrees Fahrenheit. Baking temperature. It's like baking around that temperature. So get this, yeah. So this is why you put baking soda in bread, some kinds of bread when you make it. Because what happens is it's non-spontaneous when you put it in the mix. But it hits 350, it becomes spontaneous, it starts producing that gas naturally on its own. And that's where the bread gets fluffy from. So that's where the bread gets poopy. So, but here's the deal. Once it hits that temperature, is it the temperature that's making it spontaneous? No, it's just the reaction becomes spontaneous. So when you take it out, okay, it stops producing the CO2 because it goes below that temperature, but now all that gas is in there, right? And we know gases fill their containers. So once it makes the gas and you trap it, it's always going to be puffy, like a balloon. The gas is always just going to expand. So you stick it in the oven, non-spontaneous, 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 boom, spontaneous, it starts producing CO2. So reactions that are spontaneous, they can also be non-spontaneous by altering what? The temperature. The temperature. For instance, if I put a cube of ice on the table, is it going to melt? Is it going to melt spontaneously? Yes. Do we care about rate? No. If it was a hotter room, it would melt spontaneously faster. So colder room, it would melt spontaneously colder. Now, is it possible for me to put the ice cube on the table and for it to spontaneously freeze? Yes, if it's a frozen table, if we're below the freezing point. If I walk outside of the Green Bay Packers game with a cup of water, it's going to spontaneously freeze. If I walk outside at a Miami Dolphins game with an ice cube, it's going to spontaneously melt. Okay? Same reaction. Spontaneous in different directions depending on what? The temperature. So obviously, if we want to create an equation for spontaneity, what factor has to be in the equation? Temperature. So here is the equation that describes whether or not a reaction is spontaneous or not. Where's my pen? No. It's in the... Okay, so this is called the Gibbs free energy equation. Boom. All right. So delta G equals delta H minus delta S. But I said what factor has to be in? Temperature, T. So delta G equals delta H minus T delta S. That is the Gibbs-Freon equation. That tells us if a reaction happens spontaneously at a given temperature, when taking into account whether it releases or absorbs heat, and taking into account whether or not it gets messy. So you see all these triangles around? These triangles tend to scare college students when they look at this stuff because they think it's more complicated than it is. So they get all pissed off in this unit, but to me, getting pissed off about it is actually the answer to why it's easy. Let me show you. There's a little mnemonic for remembering this. Oh God, I gotta look at Gibbs free energy. God, I hate this shit. God, I hate this shit. Alright, you see it? I swear to you, when I do, so I'll do this whole thing in class, and you'll know now, but I do this whole setup, and you guys are here so I can tell you, but I do this whole setup where I start teaching this stuff during class or on the lecture or whatever, and then there's a moment when I get all pissed off and I actually take a beaker and slam it on the ground and break it. God, I hate this shit. I'm like, God, I hate this shit. That works perfectly. You know? So I set everybody up. So you, honestly, anyone that hit me before, I get emails all the time and they're like, God, I remember. So if they ask you to solve for a problem, you just literally plug into this. Kelvin, remember, is degrees Celsius plus what? 273. Okay, so I doubt on the SAT subject you have to do anything with this, but it's a good equation to just know. Alright, so that is a little intro to thermodynamics. Let me go through and summarize it real quick. Thermodynamics is not thermochemistry. Thermochemistry deals with just delta H. Okay, thermodynamics deals with if a reaction happens spontaneously. If it happens spontaneously, it doesn't have to happen fast. At 1 degree Celsius, an ice cube will spontaneously melt slowly. And at 100 degrees, it will spontaneously melt fast. Both are spontaneous. Okay? If it's greater than 0, it's non-spontaneous. If it's less than 0, it's spontaneous. So this comes out of the equation. So you can mess with those variables to get a value here. We're going to deconstruct that a lot this year. Delta H deals with if heat's being released or not. Pretty obvious. Remember, it's a little tricky, so remember, reference this. I'm always touching this. If this absorbs heat, I feel cold. And the other factor is the disorder. Okay, we know that gases are more disordered than solids. Certain reactions, kind of like the baking soda decomposition reaction, tend to be messy reactions, but only spontaneous at certain temperatures. And that we maximize that when we bake bread. That's why baking soda has the structure it does. We need it to be spontaneous at certain temperatures. All those things come together to the God, I hate this shit equation that involves a temperature value in here. One thing I will point out, that if the delta S or the delta T is 0, the delta H is approximated by the delta G, right? Because if one of these things drops to 0, this whole thing goes out of the equation, and you can relate delta G to delta H. So if I had a reaction where I said, estimate delta G, and you looked at it, and there were 2 gases on the left and 2 gases on the right, delta S is probably around 0. It doesn't get messier or clean. So if delta S is around 0, this whole thing drops out, and you can say delta G is equal to delta H, way beyond the SAT subject. I just wanted to throw that out, okay? So that's thermo. Let's take a little venture now onto acids and bases. Totally changing reference time. Totally changing our frame of reference. Patrick, are you only doing the ones that had you circled? Yeah. Okay. Let me take a quick. You good? Strong. You good? Who's that? All right. Okay. Acids and bases. Hold on. Sorry, does anyone have any All right. So we know the pH scale. Okay. pH scale goes from 0 to 7 to 14. We know that this is the acidic range, this is the neutral range, and this is the basic range. And we know that anything that starts with an H, why don't we just call it HX? This is an acid. And things, we'll call it XOH. That's a base. Okay? Pretty simple, right? Not a big deal. This kind of acid, it has a little bit of I don't know how much you need to know about this, but all right, I'll just tell you. Okay, this acid is not just called an acid; it's called an Arrhenius acid. And an Arrhenius acid is called an H+ donor. So what that means is if you had a little solution and you put it in the solution, you're going to get H+ and A- in the solution. We're assuming strong acid right now, or whatever. That's what it means by it being a donor. It's giving H+ to the solution. This is called an Arrhenius base. And what do you think an Arrhenius base is? An OH donor. So, likewise, you get a solution and you put NaOH in it, you're going to get Na+ ions and OH- ions. There's the donor piece. Now, it's just some dude who came up with this. Don't worry, it's just some guy who came up with these names. That's what they call it. There are two other names, Bronsted and Lewis. Now, I don't know if those are on SAT subjects. So when you guys go home and you look in your little review books or you look online or whatever, if you see the name, can you write Bronsted? I'm going to write it here. And it's got a little line through it because he's like a weird European guy. Bronsted and Lewis. And I'm not talking Lewis structures. These names associated with acids and bases, let me know. And then I'll go over those next time. I'm really not quite sure. But I know Arrhenius is. Now, what Arrhenius developed was this way to relate the pH to the concentration of H and the concentration of OH. So let's look at that. So what's concentration? Molarity. So if I say like H+ concentration, that means the moles of H+ divided by what? Yeah, brackets mean molar. Not just liters, but what? Total liters of solution. And if I have concentration OH-, that means the bracket is a symbol for... Did I show you guys that in the lecture? Did I say the bracket? No? Okay, I never did that. Okay, bracket, if you put something in bracket, that equals molarity. Moles per liter. Moles of OH-. This comes up a lot in equilibrium, and it comes up a lot in kinetics when we do it, over total liters. Right? No big deal. All right. So, there is an equation for calculating the pH of a solution. And the pH calculation is the negative log of whatever the molarity of H+ is. That's the equation to get the pH. And the equation to get, there's something called the pOH. And that's the negative log of the concentration of the OH-. Just write this down. Now, do we reference the pH and the pOH? What do we always talk about? pH. High pH basic, low pH acidic. But there's another way of looking at it. Instead of referencing the acid, we could reference the hydroxide. So in the pOH, a low pOH, what do you think that means? It's basic, and a high pOH means acidic. But don't worry about it because there's a way of working around the whole deal, and I call it the magic horseshoe. Okay, there is something called the magic horseshoe, and it goes like this. You may get 1 or 2 questions on this, maybe. So the magic horseshoe says that if we can start with the concentration of H plus, and we can end with the concentration of OH minus by utilizing the pH. So if I wanted to take the concentration of H plus and I wanted to turn it into pH, what do I do according to here? Negative log of the concentration of H plus, right? We'll give you the pH. And let's say I wanted to take the OH minus and I wanted to convert it into the POH. How do I do that? Negative log of the concentration of the OH minus. Now, remember that whole pH scale goes from what to what? 0 to 14. So it turns out that you can go between these really easily, because it turns out that the pH plus the POH equals, guess, close, 14. The pH plus the POH equals 14. So the 14 minus the pH equals the POH, and 14 minus the POH equals the pH. So pH of 6, what is the POH? 8. pH of 7, what's the POH? pH of 1, what's the POH? POH of 1, what's the pH? 13. We're just jumping back and forth. Okay, now we want to be able to go in any direction. So if I go in this direction, it's the negative anti-log. So 10 to the minus pH is the POH. And going in this direction, don't worry about this, right? 10 to the minus POH is the OH. Okay, so watch this. Okay, pH is 3. What's the POH? What's the OH minus? 10 to the negative 11. Okay, POH is 5. What's the pH? 9. What's the H plus? 10 to the minus 9. Okay, H plus is 10 to the minus 1. pH would be 1. In the calculus would be. What would the POH be? 13. And what would the OH be? 10 to the negative 13. This is 10 to the negative 6. This is 6. What would this be? 8. And what would this be? 10 to the negative 8. So they could give you the pH and ask you for the POH. And they're not going to give you the H plus and ask for anything else because you're going to calculate. So you need to calculate. But it's just good to be aware that this is where it's not coming. Okay, let's also list out our strong acids. Yeah, it works out easily. So we're going to go out and make a hopscotch. I was going to chop and we're going to jump around. It's going to be kind of tight. Alright. Yeah, the horseshoe. It's tight. Alright, so let's make sure that we remember our strong acids, but we're not calling them just strong acids, we're calling them strong arrhenius acids, because we're sad like that. Okay, and strong arrhenius acids, these are also called strong electrolytes. Electrolytes are things that conduct electricity when dissolved in water. Okay? And we know that when we take a strong acid and we put it in water, what happens to it? It separates into its ions. And actually, you know how on some of those tests I would say hydrochloric acid solution, but sometimes I'd say hydrogen chloride gas. Now, what makes something an acid is actually it going into water. So if it's not in water yet, we don't even call it by its acid name. Like before sulfuric acid goes into water, we say hydrogen sulfate gas. Okay, before hydrochloric acid goes in water, we say hydrogen chloride gas, no ions there. But acids are never even found not in water. So what this would do then is if we plug this into some light bulb, this is going to make the light bulb light. Okay? And what's allowing it to light is these charges. The electrons can go through this solution. Okay, obviously this is going to be plugged into the wall, into an outlet somewhere. And it's, whatever. You get what I'm saying? The electrons are going to be able to go through the solution. And you saw that last year when you put sodium chloride in it. But you can also refer to that with acids. So strong acids can be called strong electrolytes as well. And we know that there are, just always helps to write them down. I always write them this way because you're never not going to write them this way when they're in the acid form. Acid-base chemistry. A couple little vocab words to go through with you guys. When we do acid-base equilibrium, we're going to be doing a lot of what are called titrations. Okay? They might have already done some titrations already last year. Titration is the process of adding acid to base until you neutralize the solution. Okay, and oftentimes there are some indicators that are used to see if you've reached, and I'm just going to kind of leave it at that because I don't really think that there is. It's really that important, but the lab setup looks kind of something like this. You have what's called a burette. It's just a regular what? Yeah, so we're gonna get really into it. We're gonna do like redox titration. Sorry, like redox. Whoa, just because you have to wait.
Those things with like
No, we got good ones. And we're gonna be plugging in pH meters to it, so we're gonna be creating a graph as we do it, which is pretty tight. So in this solution here, usually what we have in here is the base, and what we have in here is the acid. Okay, and what they put in here is some sort of pH meter. And ours is going to be, and you're going to create what's called a titration curve from that. And it turns out that when you titrate a strong acid, you get one kind of curve. When you titrate a weak acid, you get another kind of curve. Way beyond this stuff. The thing that's in the burette, sometimes they call that the titrant. Okay, friends? Okay. No big deal.
So the base is the titrant.
Yeah, usually the base is the titrant. And what was the dilution equation from before? Do you guys remember that? Back from last unit, if you had 2 molarities in one volume, 2 volumes in one molarity, what was the equation? Yeah, M1V1 equals M2V2. This is also can be used for titration as well. Which is why I didn't say, and I remember I subtly said this in the lecture, it's why I didn't say MCVC, MDVD. I said M1V1, M2V2, because we can use this for titration calculations as well. We can say the molarity of the base and the volume of the base equals the molarity of the acid and the volume of the acid. And we can use this to actually determine the molarities of either the titrant or the acid. Okay? So you can use this equation for both dilution, so we could say this could be used for dilution and this can be used for titration. Is that right? Okay. So what we got here with acids and bases, we got a pH scale from 0 to 14. This is acidic, this is basic. Typical acids are alkenious and acids and bases. Arrhenius acid is is a hydrogen. Sometimes a hydrogen is just called a proton, by the way, because one hydrogen just has one proton. So that word is used interchangeably. So a proton donor or a hydrogen donor and a hydroxide ion donor is the base. When we put brackets around something, what we're referring to is its concentration. The pH can be found by taking the negative log of the concentration of the H plus and the pOH by taking the negative log of the OH. Actually, in all of chemistry, this little P in front of something means you're taking the negative log of it. That's what any equation you get. So if I put the P of Ramsey, I'd be taking the negative log of Ramsey. Okay, if I put the P of smiley face, it would be the negative log of smiley face. If I put the P of Ka, it would be the negative log of Ka, which is something we'll do later. So that's a way of like a trick to get into it. There's this thing that called the magic horseshoe. No one else will call it the magic horseshoe, so don't like write that down or anything. But the main relationship is that you can jump between P's by taking 14 minus it. You can jump between any P's by taking 14 minus it. So if I have the pKa and the pKb, it's going to be 14 minus it. 14 is always a scale that works with P's in chemistry. We have our strong acids. We can also call them strong electrolytes because they conduct electricity when dissolved in water. Titration is the process of adding acids to base until we reach neutralization. And the dilution equation and the titration equation can be used interchangeably because what we have here is a concentration and a volume. And here I have a concentration and a volume. Okay? All right, last topic for today, and then we'll be almost there. This is the last one, and this is probably the one that throws people off the most when they go and try and study for this test on their own. Okay, and by the way, I'm going into a little bit more detail. They're going to ask you things like which of the following is an acid. They're going to ask you things like which of the following is a basic pH. Okay, what is the equation for Gibbs free energy? Which of the following is spontaneous and give you the values. The most difficult thing you might get is which of the following has a delta S that's positive. Just look for the ones that produce the gases. They might say which of the following is used for a titration and you choose burette over volumetric flask. They say which of the following is used for making a solution or diluting it, you choose volumetric flask, right? Because it's got the skinny top. That's the kind of shit you get asked. Okay? So this last topic is equilibrium. A lot of my research in graduate school has gone into teaching equilibrium, teaching it well. So I save this till the end. We do this right before the AP test, when everyone's just ready to go and all our other skills are strong. Equilibrium is a challenging thing to understand conceptually, so I'm going to do my best for you. Okay. You have a chemical reaction where A goes to B. Let's plot this. Okay. Here's time. And here is concentration of A. Okay? And concentration of B. We're going to plot them on the same axis. So, at the very beginning of this reaction, is it all A or all B? It's all A. So at time equals 0, it's all A and no B. That's because it's going from A to B. Does that make sense? Now, this reaction, if it were spontaneous, it would just happen, right? And if it were non-spontaneous, it wouldn't just happen. We'd have to make it happen. Okay? So either way, the reaction is going to just happen. Okay? So let's say it just happens. What's going to happen when it happens? What's going to happen to the concentration of A over time? It's going to go down. Okay? And what's going to happen to the concentration of B over time? Now, the slope of this line relates to what? How fast? Does it relate to if? No. What happens right here, the crazy, gotta hate this shit stuff that's happening right there, there's a lot of complex delta G equals delta H minus C delta S right there. That's telling us if. Once it happens, this is telling us how fast. Okay? And so don't write this, but the rest of the year is going to be broken up after this next unit into really 3 things. this point, if this point, which is what? How fast, okay? The slope of that line, if it were like this, it would be slow, right? And then it's going to be broken into what happens at equilibrium. And here's what happens at equilibrium. They both go up proportionally to one another, and then something happens like this. This line, this is called equilibrium. So what happens at equilibrium just by looking at that graph? Okay, they don't, they balance out, but do their concentrations become the same? No, they just, over time, what happens to their concentration? It stays the same. Over time, the concentration stays the same. Doesn't mean the reaction is not happening, but it means this. Right here, in this whole area here, it was, and just bear with me here, me and Tim right here. Okay. Right here, it's A goes to B. Is it possible over here for it to be A goes to B? No, because if it were A goes to B still, what would be happening to these levels? A would still be dropping and B would still be going up. It would be like crossing, right? Fully. That's not what happens here. It's subtle. What's happening here is this. And that's chemical equilibrium. Is A still going to B? Yeah, but what's B doing? Going to A. So the rate, the speed at which A makes B is the same as what? As B makes A. That's equilibrium. So what we have right here, kind of right here, is this. Do you guys see what I mean by that? See what I mean by that? They're starting to level out, right? But they're not fully leveling out. See, A is making B, B is making A, but not the same speed at which A is making B. So it doesn't level out yet. So once we've reached equilibrium, A makes B, B makes A. Okay? A makes B, B makes A. A makes B, B makes A. A makes B, B makes A. At the beginning, it's just A makes B. Done. Okay? As it approaches equilibrium, A makes B, B makes a little A. A makes B, B makes a little A. And then A makes B, B makes A. A makes B, B makes A. And that's chemical equilibrium. And that is important. It doesn't happen all the time, but it's hella important in our body. How the hell does our body maintain a pH of exactly 6.8 at all times? Like when you get altitude sickness or you have diabetes or something weird happens, you have a panic attack or something, all that's happening is because the pH inside your body is changing because equilibrium is thrown off. So acid-base chemistry and equilibrium are hand in hand. Okay? So this value here, this is called KEQ. Okay? KEQ is defined as that ratio, the ratio between products and reactants when they've reached what? Equilibrium. The ratio between products and reactants when they've reached equilibrium. So let me show you how you draw that. If we have a reaction, let's say 2A plus 3B goes to 4C plus 5D. And I want you, and it's an equilibrium. I want you to write KEQ for this. You just write it. You're not going to draw the whole graph. That whole thing was conceptual, okay? Here's how you do it. KEQ is defined as the concentration of the products. It's a random number, okay? So, I feel like I need to emphasize something right here. It's reached equilibrium, right? And at equilibrium, the concentration of this isn't changing and the concentration of this isn't changing. Are you with me on that? Now we just need some way to represent that number. We could pick a lot of different things, but what needs to be in that number? What two things have to be in that number? The concentration of who? A and who? B where? At equilibrium. So the two things that have to be in that number are this value and this value for A and B. They have to be in that number. So it can be A minus B, it can be A times B, it can be B over A, it can be A over B, it can be anything we want to get one number, but we got to do the same thing for all equilibrium. Okay? So we can compare reactions. So what they chose, ambiguously, was to do this. To take products at equilibrium and divide it by reactants. This is at equilibrium, though. It's not. This video actually should be good for you to review for this class later. It's not anything. It's not just random. It's at equilibrium. And what they do is it's raised to the power of the coefficients, because we need these to play in also. So here's how we write it. Who are my two products? C and D. And what's the coefficient for C? 4. And what's the coefficient for D? 5. See what we're doing here? And the numerator is going to be A. What's the coefficient for A? 2. And what's the coefficient for B? 3. So that's the KEQ for that reaction. And now when you go back and look at the problems, you might have looked at it and it says right for KEQ, you freak out. That's all you do. So let me ask you guys to do this. I want you guys to write the KEQ for this reaction. I'm going to write one right here. Okay? So 2 HCl plus Na2CO3 aqueous is at equal to, don't worry about the charges, I'm just writing something out now, is equal to CO2 gas plus H2O liquid plus, what else do we make? NaCl aqueous. And is that fully balanced? No, because I have to do that, right? So I want you guys to write the KEQ. Sorry that it's all messed up. Write the KEQ for that reaction. So who's going on the numerator? Concentration of CO2 raised to what power? 1. Concentration of H2O raised to what power? And concentration of NaCl raised to what power? 2 over concentration of HCl raised to what power? 2 over concentration of Na2CO3 raised to 1 power. Congratulations. That's it. So, where the hell would these numbers come from? They would say to you, straight up, the concentration of CO2, H2O, NaCl, HCl, and Na2CO3 are the following at equilibrium. Calculate KEQ. So you write that and you freaking plug the numbers in. And you do the exponents and you multiply them out and that's it. Done. You okay with that? Now they're not even going to ask you to calculate that. They're going to give you the reaction and ask you to write that. And they're going to flip it around. They're going to make them all added. They do all kinds of stupid stuff. Yeah.
Wait, so what they're giving you is they're giving you the molarity of all those?
Yeah. So what this is okay. Conceptually, the concentration of A. Let's say the concentration of A is 2. And let's say the concentration of B is 2, or is 1 at equilibrium, okay? So let's say that this value here is 2 and this is 1. So for this reaction, it's B over A, because the reaction was A goes to B. You guys with me on that? Okay, so if I wanted to get a number for this, I would say concentration of 2 divided by concentration of 1 equals 2. So what that tells me is that at equilibrium, for the reaction A goes to B, the ratio of product to reactant at equilibrium is 2. So what that tells me is at equilibrium, this reaction no, I screwed up. Right? What did I screw up on? So what this reaction, this number tells me that this reactant, the product is less than the reactant at equilibrium. So it tells me that this reaction is reactant heavy. Means at equilibrium. Leave it.
Sorry.
I'll have it posted. No, bye. Okay, cool. It'll be posted. Okay. Bye-bye. So either way, you're not going to have to do that kind of calculation. You will in our class, I'm sure. Okay. You okay with that? All right. So that's equilibrium in a nutshell. Now there's one last little piece that I'm just going to show you because we're on a roll right now. All right, let's draw this little graph again. A goes to B at equilibrium. So we're going to make it look like that. A, B. Okay? We have point A, we have point B, and we have point C. Where is it at equilibrium? Point C is at equilibrium. This reaction is reactant heavy at equilibrium because the A line is higher than the B line, whatever. Okay? Now, I need a volunteer. Alright, this is my friend, Woody. And somebody actually drew a little TV on it. Alright, so, Eugene, get up here. Alright, so, Eugene and I are a chemical reaction, okay? So, Eugene is going to get on one side, okay? And I'm going to get on the other side, okay? And we're going to sit on this, right? Now, we're not at equilibrium. So what do we have to do to get back to equilibrium? We have to shift around, right? So I'm going to move in. Look at Eugene. We're going to try and get it so we balance. So we're going to get, okay. Oh, no, so I got to move back a little bit. Oh, no, I got to move back a little bit. Okay, there we almost.
Eugene, you have to move
forward. Are you okay? Come on, we gotta want it.
Why did I not bring my camera today?
Oh my god. Alright, let's pretend that Eugene and I right here found our equilibrium. Our KEQ would be defined by this distance between him and me. Metaphor. You guys with me on that? Okay, that's our equilibrium position. Now, the tricky thing is, what happens if one of you came up and put a ton of bricks on me? Are we going to shift away from equilibrium? Yeah. And then what are Eugene and I going to have to do to get back to equilibrium? We're going to have to shift to refine our equilibrium. It's going to be a new place now. With me on that? Okay, so thanks. You can get off. So we'll play with this a lot when I get to equilibrium. So that relates to this. If I come up here and I take a reaction that's equilibrium and suddenly I say, boom! You added a bunch of A. Okay? This thing here is a constant. So what the hell is going to happen to B? B is going to have to go up too until you reach equilibrium. What am I trying to do with this distance? I'm trying to keep it the same. I'm trying to keep, this is KEQ1, and here is KEQ2. I want KEQ1 to equal KEQ2. I want the equilibrium position to never change. What happens if this goes all the way down here? I pull a bunch of B out. What's going to happen to A? It's going to shift down until it gets bad. So notice, I could care less what the concentration of A is and what the concentration of B is. What is it that I care about? The KEQ stays the same. And KEQ is a function of their proportion to one another, not their anything else. You guys with me on that? Okay? So this whole thing, this is called a shift. This right here, this is called a shift. And what is the reaction shifting to? What is it keeping in mind? What's its sensor? What is dictating how much it shifts? The value of what? Not just the molarity, the value of what value? KEQ. KEQ is saying that it needs to stop here because this has already gone down to here to keep that value the same. That is what it cares about. And we should, this is all being recorded here. Okay. So this thing, this shift, this is called Le Chatelet's principle. Some French narcissistic racist asshole, okay? Named Le Chatelet. Alright, seriously. This guy doesn't have a pretty past. But he was the dude that came up with this principle. Can't believe I'm going to post this online. I'm totally dropping S-bombs. Whatever. Fire me. Alright, it's Le Chatelet's principle. And Le Chatelet's principle simply says that a reaction will do what to make its KEQ stay the same? It'll shift. The reaction will shift. And there is a really easy trick to figure out how it shifts. And just like, what was the trick with the thermodynamics equation? God, I hate this stuff, right? Right? So the shift for this is the Superman trick. So, up, up, and away. Or down, down, stay. So here's what I mean by it. Let's say we take a reaction. A plus B is at equilibrium with C plus D. And your answer is either going to be right or left, or you could say to the products or to the reactants. But I want you to use this idea, Le Chatelet's principle, as your guide. So watch how simple this is. Okay, seriously share this with other people, because this is like the one thing that makes this work. A random survey of college students said Le Chatelet's principle is the hardest thing for them to understand conceptually. Not at all, okay? So if we have a reaction, okay, and we increase a bunch of A, okay, the reaction's at equilibrium, and then suddenly somebody pumps a bunch of A into the system. Just like putting a bunch of bricks on me. What's the reaction going to do? Shift to keep what the same? KQ, right? So the rule is up, up, and away. So if A goes up, which way is it going to shift? Away. Up, up, and away. So the reaction shifts what direction? Right. Which is the same thing as the products. Okay? So, if you increase A, the reaction will shift to the right, to the products. Feel me on that? Let's do another one. Let's say we increase D. Go over here. Up, up, and away. Which way is it going to shift? Okay, it's going to go left, towards the what? Reactants. See what I'm doing, guys? It's simple, okay? And it makes sense. If you put a bunch of D in the system has too much D. So the reaction is going to shift away from it to get rid of it. If you put too much A in the system, the reaction wants to get rid of the A. So it's going to shift away from A, convert some to B to keep that ratio the same. Ratio is the same. A goes up. B's got to go up also in order to get back to the same. Okay, now let's look at it from the other direction. Let's say we decrease B. Okay, down, down, stay. So it shifts to the same side it's on. Okay? So if I decrease B, is it going to go left or right? Left, which is the reactance. So when I say stay, I mean shifts to the side it's on. That's what I mean. Okay? What if I decreased C? Down, down, stay. So which way is it going to shift? To the right. So if you decrease C, it's going to shift to the right towards the products. So reactions that are equilibrium will shift to maintain their KEQ. The way we figure out the direction they'll shift is this real simple thing. If you want to memorize another way, you can say if arrow is going up, the other arrow is going to go away from it. You're going to go head to tail. If the arrow is going down, you're going to go head to head. Down, head to head. Up, head to tail. So let me show you an actual reaction on this so you guys can figure it out. So let's say we have this reaction. Let's do a net ionic reaction. H plus Cl minus is at equilibrium with making HCl. Okay? So the question I'm going to ask, no, that's stupid. I don't want to do that one. Sorry. What's a better reaction? H2 gas plus O2 gas goes to H2O, make it all gas. Okay, first off, could you guys write the KQ expression? Write KQ. All right, so who's on the top? H2O raised to what power? 2. And who's on the bottom? H2 concentration and O2 to the first power. So what the whole reaction is trying to do is whatever number this is, it's trying to keep it the what? Same. Okay, it's trying to keep it the same. So my question is, which direction does the reaction shift? If I take this reaction is happening, let's say, inside a vessel, like a container, and I poke a hole in it, and I inject a bunch of oxygen gas in. Which direction is the reaction going to shift? Where? To the right. If you increase O2, I pump a bunch in, up, and away, shift. So it goes right, and that is the direction towards the product side. Can you guys give me 2 ways to make the reaction shift left? Think about it for a second. 2 ways to make the reaction shift to the left. Okay, one way would be to decrease the amount of oxygen. Okay, that'll make it go left because down, down, stay, or shift in that direction. What's another way to make it shift to the left? Yep, increase the concentration or the amount. In this case, we can say concentration because we have a gas here, of H2O. That's going to make it go left. Okay? So, these are the kinds of questions they'll give you. They'll say, which of the following will increase the products? Or which of the following make it go to the left? Or what will happen if you increase add a bunch of oxygen? One little side thing, if I pumped in a bunch of Ne, neon, what do you think will happen? Yes. Nothing. Because Ne is not in here. The neon is not going to react with anybody. Okay? Neon is Regina George, right? Not going to react with anybody. So all it's going to do is pressurize the system equally for everybody. And the reaction is going to do the same thing. Okay? So,
But what if we added something else
other than what?
gas?
Okay, if you add anything that's not up there, nothing happens. I use that just as a Okay, so we talked about thermodynamics, and the major thermodynamic equation was the Gibbs free energy equation. And the reason we derived this is I said, wait a sec, we got this baking soda crap that gets messy. It's a delta S positive reaction, but it's only spontaneous at high temperatures. So it's got to be a temperature factor in there. The trick has got to hate this stuff. All right, we looked at acids and bases, and we said that there's this easy equation to move in between POH and pH when we look at Arrhenius acids and bases, and it was that relationship where pH plus POH is 14. We said the strong acids can be called electrolytes as well. Titration is used as a neutralization technique. We looked at an equilibrium, and when they level out over time, they're at equilibrium. You're still making B and you're still making A, but the rate at which you make A and B is the same. When you get away from equilibrium, like seen here in these graphs, you can shift, and that shift is called Le-Chat-Delay's principle. And that shift is a very, very strategically easy thing to answer to get the question right. If you increase something, you're going to shift away from it to decrease its amount, up, up, and away. If you decrease something, you need to replenish it, right? So everything's going to shift towards it to say, oh, you lost some B, how sad. Let me shift over here and give you some more B. Okay? The whole goal is maintaining KEQ, though. Okay? So what time can you guys meet next time? I'm toast. What time can you guys meet next time? Can you guys do, I can't do Tuesday after school, but I could do Wednesday, Thursday, or Friday. I can just declare it right now and you guys work around me. Would that be easier? Yeah. Okay, cool. Let me just start. I'm keeping this recorded so people who watch this can hear. So why don't we do Wednesday, directly after school, whatever day it is? What kind of day is Wednesday? The blue day? Grades are due, so I can't do it in the morning. So can you do it after school on Wednesday? If you guys? Or do what? Okay. We could do, well, we're almost there, so we don't have that much more to talk about. So we could do Thursday after school. Want to do that? Okay. Okay, what I think I'm going to do is probably at that point start giving you guys some practice problems. Because I don't think, if I count what you're learning from me in the next 2 weeks, I don't think we have any more topics to do. I think we're pretty much screwed. If you count what you learned from me, you count everything you learned last year, I think we're pretty much screwed. So, other than people that used to getting the thermo stuff from people that you missed and acid-based stuff, and not getting the stuff from last time. Yeah.
How much of the old stuff?
So a lot of the test is you're going to have like tons of nomenclature. You're going to have tons of stoichiometry balance. So I would say that about 60% of the test is stoic, balancing, gases, all that kind of stuff. NC, delta T, heat equals NRT, all that kind of stuff, heat flow, like every single thing you learn last year, and another 40% is this, but you ain't going to get into 700s unless you do this over. Okay, so you're just not. So what we're going to need to do is look at the way they ask it. But there's, in terms of the stoic, it's all like whole ratio stuff. They're not going to make you do like that much, like complicated conversions and stuff. They just want to see if you can do the basics, empirical formula, that kind of stuff, percent composition, shit like that. Okay, so we got it all.
Yeah, we took summer camps.
Well, just remember that I've been asking you guys a lot of stoichiometry questions in 3 months before. So like when you took today's test, you had to do a grams to mole from. That's kind of stuff last year. Okay? You had to, I said, what mass of this is produced from this? That's stoichiometry. And I'm asking you those questions. I'm not writing them. These are all 80 questions. So that's, if you did today's test, you're fine on the stoichiometry on this. Like, don't think that, remember on the practice test, I asked you a question or in the learning packet, what's the percentage of oxygen in potassium oxide, right? That's what I mean, that's percent composition. That's it. Right, so there's not really, all of the stoic that you need to know for this, we've been doing in this unit. All of them. Okay, I promise you. Yeah?
It wasn't like, usually where it's like, if like, you have to say like it's true, false, like it's true.
Okay. That's great. So since I think you guys have an appetite for that, you might want to go do some practicing. Let me show you what I mean by that. I was planning on going over that when I do the when we do practice problems, but let me just really quickly answer that question because I want to make you feel it. So the test is divvied up into two parts: multiple choice and true-false explanation. Okay. So the way the true-false explanation problems go is they give you one statement, they give you another statement, okay, and then they ask you if it's a correct example. Okay, so you look at all of them.
I gotta leave and I have a couple of students finishing up a test and a student.
For sure. Yeah. So you look at each of these in terms of whether it's true or whether it's false. And then you choose if it's a correct example. So it's like 3 separate problems. Here's how it works. They give you a statement, number 1. You look at it individually. Okay? True or false. Okay, so it'll say the shape of carbon dioxide is bent. So it turns out that that is false. We're doing that. Okay? Carbon dioxide is linear. Carbon dioxide is linear because there's no lone pairs on C. Okay? So like
Water is bent.
yeah, water is bent. So here's water because these lone pairs, and here's carbon dioxide. Okay? So they'll say carbon dioxide is bent. True or false? False. Okay? Once you answer false, it cannot possibly be a correct example. That's off the limit. No way. Okay? Second question. They'll give you something else. They'll say now something else related to it. They'll say carbon dioxide is non-polar. Okay? Turns out that's true. Because, and we'll learn later, because its shape is symmetrical. Okay? And because it actually is very easy. Pairs on the central atom make something polar. No pairs on the central atom makes it non-polar. Okay? So this is non-polar. That's a true statement. But since the first one was false, we can't do that. So what we would have in this is we'd have false, true, and we wouldn't answer them. Okay? The absolute, yes, you can sit down anywhere here. The absolutely only way you would bubble correct examples is what? They were both true, but the second one actually explained the first one. So for instance, the statement 1, the symbol for sodium is Na. True. Statement true. Statement 2. Sodium has 11 protons in its nucleus. Just look on the periodic table. It's atomic number. You don't have to know that. It's 11. So true, right? Does that correctly explain why the symbol's Na? No. No. What would be the correct one is if they said the symbol for sodium is Na, right? And then in the second one they said because some weird people decided to use Latin to label the elements, right? Then that would be true, correct example. You know that, right? So you have to look at them all individually, and then you say, so here's one of them. If I were to say the shape of carbon dioxide is linear, what would you say? True. And for this one, I would say carbon dioxide has no lone pairs on the central atom. True. And that is a correct example. The reason it's linear is it has no lone pairs on the central atom. It is the lone pairs on this central atom that push it into its bent position. So they could say something like, you know, hydrochloric acid is a strong acid. True or false? True. Hydrochloric acid fully ionizes when put in water. True and correct example. That's what makes it a strong acid, that it fully ionizes when put in water. So that's all you do. So what you do to do those problems is what I always tell people to do is go through and do all the first row first. Okay? Then go through and do all the second row. Okay? For any of them that you got false on the first row, don't even look at the correct examples. For any of them that you got trues on both, then start looking for the correct examples. And you have 15 of those, I think. So that's the answer to your question. So that's actually a really easy way to study this stuff is open up a book and just look at those. Because it's not like they're really easy, quick little facts and stuff. It'll be things like a burette is used with titration of truth, you know, that kind of stuff. Like,
would it be easier to just go do just the first and second row at the same time?
yeah, right? Yeah. I mean, when I do stuff, I like to do it in an ordered fashion. So whatever works for you. Like, when I sit down to do this stuff, I'm always like, what intimidates me about this problem is the way they make you think about it all kind of in different angles. So what I would want to do is I would want to maximize correct points. So they're giving me a point every time I mark one of those right. I don't have to get the whole group right. So I would get a point for that one, even if I got the two right. So in my mind, I'm trying to pick up points. So I'm like going through and looking at all the ones, true, false, 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 and then looking at it rather than getting locked in. So that's a test-taking strategy, but I think we're thinking about it more with what makes sense. Cool. So we'll meet next Thursday and we'll count out a bunch of practice problems, do that again, and then I think by then you'll guys will have this all together. Okay, is that helpful? Okay, cool. All right, this one is definitely going to YouTube right now.